Okay, we are live. Excellent, excellent, muy excelente. So, standard state, not not the most difficult thing in the world. Enthalpy is sensitive to external conditions. Okay, remember, enthalpy is the heat of reaction at constant pressure. So technically, it's delta E plus P delta V. Remember. Now, because enthalpy is sensitive, what that means is it takes energy to change the temperature of something. It takes energy to compress it. It takes energy to melt it. If you get to, if you do something, almost anything, to change the way things are happening, like the conditions that things are happening in, then that will have a big impact on the enthalpy of a reaction. So look here, we have propane reacting with oxygen to produce CO2 and H2O, with the enthalpy change being negative 2044 kilojoules per mole. Here we have propane plus oxygen reacting to produce carbon dioxide and water, and the enthalpy change of our reaction is negative 2220 kilojoules per mole. Why the difference? Well, the difference is right here. We're producing gaseous water, and here we're producing liquid water. The reason that this one up here is giving off less energy is because some of that energy was used to make the water a gas. This one's giving off more energy because it didn't do that. Okay, the water remained a liquid. So we have what are called standard conditions. This is the temperature, pressure, concentrations that we call standard conditions. Okay, it was chosen as a benchmark. So that way we can compare different reactions without having to constantly recalculate and take into account the fact that, they're taking place under different conditions. We don't actually know how these compare. So the standard conditions mean that we can compare things. So these conditions are 1 atmosphere of pressure, 1 molar concentration, and normally 25 degrees Celsius. I say normally because this changes a lot. Okay, sometimes it's 20 degrees Celsius. Sometimes it's 0 degrees Celsius. Okay, so when people report that something's happening at standard conditions, you still have to look and see what they mean by standard conditions. They'll usually report that. Your textbook, I checked, gives it as 25 degrees, while also noting that it sometimes changes. So your textbook, those problems, they're going to be at 25 degrees Celsius. Room temperature is what they mean by that. 25 degrees Celsius, depending on where you live, is chosen as room temperature. And 1 atmosphere of pressure is the standard so that you can do normal stuff there. 1 molar concentration, that's mostly about math. All right. So you know something is at standard conditions if you have a little dot. Okay. So this here is a delta H without the dot. This here is delta H with the dot. Okay. When you have that dot on a thermodynamic quantity, you know that it's taking place under standard conditions. Okay. Which means that you can use that, more generally. There is a way to compensate for the changed conditions, and I don't think we're going to be talking about that, but there are ways to do that. So these, I did it again. These are all thermodynamic quantities. Enthalpy, internal energy. You'll notice that I left the U instead of E, whatever. This is entropy, and this is what's known as Gibbs free energy. We like all of these things. They're very important. And they can all take place at or away from standard conditions. And these all have the dot, so if we were talking about them, then these would all be at standard conditions. And the fact that enthalpy is sensitive means that you're going to have to be pretty careful about the state of matter that something's in, gas, liquid, or solid, because that will change what we call enthalpy of formation. So be careful about that when we get there. We'll get there later on this weekend. So that is standard conditions. 1 atmosphere, 1 molar, 25 degrees Celsius. All right, so now let's go ahead and continue to talking about the enthalpy of a reaction. So, delta means final minus initial. And because we're talking about state functions, that means that it doesn't matter what path we take. So long as we can get from A to B, then we're good. We just do final minus initial. So for example, here we have the enthalpy of fusion, which is how much energy it takes to melt something. So here the enthalpy of fusion of water, going from solid to liquid water, is 6.010 kilojoules per mole. Note, it's positive. Melting is an endothermic process. Then here we have the enthalpy of vaporization, going from liquid to gas, is 40.660 kilojoules per mole. So what is the enthalpy of sublimation for water? How much energy does it take to go from a solid directly to a gas? Well, like I said, it doesn't matter what path we follow. Going directly from solid to gas would be sublimation, but in the exact same vein, we go from solid to liquid, then liquid to gas. That would work just as well. So all we have to do is add these two numbers together, and that would give us the enthalpy of sublimation, 46.670 kilojoules per mole. And this is true for any process. You could do it for 2 steps, it could be 3 steps, it could be 5, 15, doesn't matter. So long as you get from A to B, it'll work just fine. This is an example of Hess's law. We'll get into that more later. So, how much energy is needed to melt 23.49 grams of ice at 0 degrees Celsius? Well, boop. You'll notice that this is the enthalpy of fusion, and it doesn't say, it doesn't have the little dot there. Okay? Because when they do these enthalpy of fusion, enthalpy of vaporization, they are reporting it at the condition where it ordinarily occurs. So this would have been measured at 0 degrees Celsius, and this would have been measured at 100 degrees Celsius. All right, so how much energy is needed to melt 23.49 grams of ice at 0 degrees Celsius? Well, we turn this guy on. First, we're going to need to calculate the number of moles of water we have. 23.49 grams times 18.02 grams per mole. Okay, now you can see it. Let me bring up Mr. Calculator. Come on, buddy. 23.49 divided by 18.02 means we have 1.304 moles of water. So we come back here, and we see the enthalpy of fusion is 6.010 kilojoules per mole. Okay, so once again, so we multiply this by 6.010 kilojoules per mole. The moles will cancel, and we'll be left with just the energy. So 1.304 times 6.010, 7.837 kilojoules of energy to melt ice, to melt 23.49 grams of ice. All right, that is a pretty significant amount of energy. That's, 7,800 apples, right? All right. So our other problem was how much energy is released by the condensation of 1.281 kilograms of water vapor at 100 degrees Celsius. Well, 1.281 kilograms is 1,281 grams. We divide by the molar mass of water. It's still water, regardless of what state it's in. And we have 71.09 moles of water. And now we multiply that by the enthalpy of vaporization, 40.110 kilojoules per mole. It gives us our answer, 2,851 kilojoules of energy. That's a lot. Yeah. Okay, that's why it takes so long to boil water. All right, so that's just, oh, you couldn't see any of that. Boom. Okay, now you can. I got it. All right, so 1.281 kilograms is 1,281 grams, is 71.09 moles, times the 40.110 kilojoules per mole gives us 2851 kilojoules. Paul decay. Now, enthalpy of reaction. We can do the exact same thing for reactions. When aluminum metal reacts with rust under standard conditions, the result is aluminum oxide and molten iron. Will the reaction be exothermic or endothermic? Okay. This is the thermite reaction, and it is pretty awesome to receive. Like I said, it produces molten iron. They use this very carefully to weld railroad ties, not railroad ties, but railroad sections of railroad together so that they don't fall apart. All right, now, is it exothermic or endothermic? Well, the answer is hidden right here. Okay? It produces molten iron. In other words, it releases so much energy that the iron that is produced, the iron that's produced is molten. That is to say, it's melted. It is liquid. Okay, so it is incredibly exothermic. But that's not what this reaction is. This reaction is iron reacting with aluminum oxide to produce iron 3 oxide and aluminum metal. So, if aluminum reacting with rust is incredibly exothermic, then the same reaction going in the other direction will be endothermic. Okay? You would have to put a lot of energy in to this reaction in order to get it to proceed. Ordinarily, it would not happen. So, how much heat is evolved by burning 10.32 grams of ethanol? The enthalpy of the reaction is negative 1366.8 kilojoules. Okay, so for this one, we're going to need our balanced reaction. Okay, so ethanol is C2H5OH, and that reacts with oxygen to produce CO2 and H2O. 2 of these, 3 of these. Actually, that would work. 2 and 3. That means we have 4 plus 3 is 7, so we're going to need 3 oxygens there. All right, so there's the balanced chemical reaction. 1, 3, 2, 3. Okay, so again, we're going to need to convert from grams to moles. So 10.32 grams divided by the molar mass of ethanol. Bring up the calculator. Let's do 0.011 times 2 plus 1.0079 times 6 plus 15.999. Divided by 46.07 grams per mole. So 10.32 divided by 46.07 gives us 0.2240 moles of ethanol. And we look at this example again. We bring it back up. We see that the enthalpy of reaction under standard conditions is negative 1,366.8 kilojoules. So multiply by negative 1,366.8 kilojoules. But you'll notice that I didn't say kilojoules per mole. When you do this, you have to take into account the fact that different numbers of moles of things are going to be produced in the reaction. When you burn ethanol, you only consume 1 mole of ethanol, but for every 1 mole of ethanol, you're also going to consume 3 moles of oxygen. So what this enthalpy of reaction means is that every time this reaction occurs, it will release, this amount of heat, but it is per 1 mole of our ethanol. If I was asking about oxygen, then it would be per 3 moles of oxygen. Okay? If I was asking about carbon dioxide, it would be per 2 moles of carbon dioxide. So you'd be dividing this number by 2 or by 3 or by what have you. In this case, because it's ethanol, it occurs for every 1 mole of ethanol. So, bring up Mr. Calculator. Now we're going to multiply by 1366.8, which means that this reaction will produce negative 306.2 kilojoules of energy. Okay. So that is the heat evolved by burning 10 grams of 10.32 grams of ethanol. All right. Third example. What amount of energy is needed to split 29.284 grams of water? I was obviously having a little bit of fun with this. Okay, so here we have the reaction for combining hydrogen and oxygen into water. But what I asked was, how much energy do we need to divide the water? So that means that the reaction is going to be reversed. So the actual reaction, the one we're looking at, is H2O splitting apart into hydrogen and oxygen. Okay? And when we do that, when you reverse the reaction, the enthalpy of the reaction, it's going to be the same number, but you're going to reverse the sign. If you release 471.6 kilojoules of energy per mole, or per 2 moles of water, then you're going to instead, if you're splitting the water, you're going to absorb that much energy. Okay? So all we do is we flip the sign. Flip the reaction, you flip the sign. All right. So 29.284 grams of water times, let's get a slightly more accurate, 1.0079 times 2 plus 15.999, 18.015 grams per mole. We're dividing. All right, so 29.284 divided by 18.015 is 1.6255 moles of water. So now, with our number of moles firmly in hand, we can multiply by the enthalpy of reaction. But notice that we're going to have to normalize it. Okay, so we multiply by the enthalpy of reaction, 471.6 kilojoules for every 2 moles of water. Okay, don't forget that you need to do that. It is super duper important. So we take this number here, we multiply by 471.6, and then we divide by 2. Okay? So 383.3 kilojoules of energy. So in order to split a little less than 30 grams of water, you have to put in a little, about 383.3 kilojoules of energy. All right. So those are examples of just working with reactions. It's just like working with any other kind of number. The complication that you need here, that you need to remember from this, is that you're dividing by the coefficient every time you work with one of these things. Later things, we'll see that the way they've set it up makes it simpler to work with, because when we get into Hess's law and enthalpies of formation, a lot of times they've deliberately set things up so that you don't have to worry about that quite so much. But in an enthalpy of reaction like this, you do have to worry about that. Now, this week's lab, the online lab, once again, you don't have to worry about that because the reactions that they've chosen for you to work with, the solvation and the neutralization reactions, those all, 1 to 1 to 1 to 1. So it's a complication that's not going to show up in lab, but it is one that is showing up in class. So just be aware that this is something you need to remember. All right. And with that, we are done with this set of slides. We're done with the videos that I plan on working on tonight. Tomorrow, I will do another 4 about enthalpy of formation, or Hess's law, bond enthalpy of formation, bond enthalpy, and heat of combustion. So we're going to be doing a lot of enthalpy stuff tomorrow. Okay? Hess's law to heat of combustion, all sorts of enthalpy. And then on Sunday, we'll talk about spontaneity, entropy, and the build-up to Gibbs free energy. Okay, with that, I am done talking, so I will see you